This laser is emits light at 405 nanometers, which is on the edge of what humans can see, but it's still definitely visible. And it is rated at 200 milliwatts, which is technically a class 3B laser. So before I get into this video, if you are using a laser, use proper safety equipment, of course. And in general, don't try this at home, blah, 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 don't have to cause all. The laser itself, because it's in such a compact package, is a semiconductor laser diode. In this case, it's based off of gallium nitride, and the diagram of that is right here. The gallium nitride is sort of a lasing medium. The general idea of a laser is to have some substance, like the original laser was a little ruby rod with mirrors on two ends of it. One mirror had a little hole, and then there was like a light coiled around this ruby rod, and it was, I think it was taken from the bulb from like some camera, or you can think of it as a light like that, where it'll emit a lot of light in a very short amount of time. And what will happen is the electrons in the ruby atoms will jump up to a higher energy state, and then in order to fall back down, they have to release a photon of some very specific wavelength. And what ends up happening is these photons sort of bounce back and forth because there's the mirrors there, and then they sort of gain energy. Well, they don't gain energy, but they build up, and then they'll slowly be released out here. It'll be a focused beam because it's such a small hole, and also only be one wavelength. And so that's sort of the original laser. But obviously all that is fairly large, and this laser is like pretty small, so how does it all fit in there? This is how. Now you see the gallium nitride, that's acting as our ruby in this case. And because there's no like there's no light source in here, that means the source of the energy that's causing the electron inside the gallium to raise an energy state is electricity in this case. Basically, we're running a current on the sides of it, and what that does is it causes photons to jump from the other side because of a charge difference. And that then causes the photons to bounce around, and then there's a hole somewhere on here, and then photons are released. So that's how the gallium nitride laser works, a semiconductor laser. Because this laser is in the 405 nanometer range of emission, it's not going to be, obviously it's not a super expensive laser, so it's not going to be purely 405 nanometer light, but for the most part, it's going to be that wavelength, which is sort of on the edge of what humans can see. I think the cutoff is around 380 nanometers. I'm not sure about that though. Please correct me in the comments. But because of that, and the fact it's only 200 milliwatts, makes it so you can't really see the beam too well. The dot is very easy to see, but the beam itself is kind of difficult. Now, a way to illustrate the beam easily is by just blowing some dust in the air where the beam is occupying, which is what I'm about to do. Hello everyone, I'm Enzo Carter, and this is Enzo Science. Today we're going to be talking about the laser I just bought. It's right here. So this, let me just put the key in because, shoot, the key fell off. Okay, that's a minor problem. All right, this is what the beam looks like. And now I'm gonna blow some dust through it. So let me go find a shelf I have neglected and grab some dust. All right, I grabbed some dust. Just gonna hold the beam here. Shoot. Yeah, so you can see the beam sort of lighting up. I'm gonna see if I can grab some more dust. I just wiped my nose with that, man. That's gonna end well. really need to clean my room more. Alright. Make sure it's not pointing at something reflective. That would be a problem. Yeah, so inside this box here, I'm going to call it Pandora's box, is a radium clock. Now, you can't really see it, and neither can I, but it is probably fluorescing to some degree. Don't worry, don't try this at home, don't touch these things, they're kind of dangerous. But it is fluorescing to some extent, because the radium, much like this laser pointer, is elevating the electrons and whatever the fluorescence is to a higher energy level, and in order to settle back down, they need to release a, in this case, green light. Well, my laser is going to do the same thing. It's going to stimulate whatever's on there. Let me just see if I can put the key in like this. Okay. As you can see, I have stimulated the heck out of all of these, and they've been glowing for a little while. I mean, I probably shouldn't shine it on the white part too much because, you know, it's like reflecting back at my eyes, and it's not good for health, but, I mean, you get the idea. I don't have a Geiger counter on me in order to show you how radioactive it is, but I think from, like, the edge of the glass, it's about 3,000 CPM. I forget what that is in sieverts. That's pretty cool, though. Oh, we're gonna put it away now. Good. So the final thing on here will be this. So why did I buy this laser? The reason is not for this video. This is just sort of a byproduct of that. But the reason I bought this laser pointer is because I want a higher energy pump. So if you haven't been with my channel in a while, and I might put something in one of the corners that links to this video, I made a video about how I did an experiment with something called spontaneous parametric down conversion, or SPDC, which is sort of like, it's also called frequency doubling, and it looks like this. So you have this, which is our non-linear crystal. This is our non-linear crystal, and in my case, it's a beta barium borate one. And you'll have this pump laser, right? And it's going to be 405 nanometers, just like the one I have. Alright, and once it enters the nonlinear crystal, there will be, in this case, this is going with type 2 SPDC. There's a type 1 as well. Type 1 requires 2 nonlinear crystals. In this case, I'm demonstrating type 2, which is what I'm most likely going to be using for my experiment. What's going to happen is these guys are going to fly off along with transmission. Now, this is just the pump being transmitted. The same laser beam being just going right through it, just like if it was going through glass. Probably would slow down to some degree, but anyway, because this interaction where it down converts is somewhat rare. I want to say it's somewhere around 1% of the time it happens, but don't fully quote me on that. These two red beams represent the down conversion. So we've got a 4 or 5 nanometer laser, and when it gets down converted, in order to conserve the energy and momentum, two things happen. One thing is they become 810 nanometer photons. They're half the energy, or in this case, double the wavelength. They go from this crystal much larger, or at least twice as large. But the other thing that happens is you notice they're kind of flying off at an angle and not completely straight. This is a conservation of momentum thing. So if you take the angle of this and the angle of that and you sort of add them together, it'll end up looking like that, which gets you back at where the beam is. But I want to say it's about 3 degrees off of where the pump is. Anyway, so that's fun. Really, really brief. Please, if you want to actually learn something about SPDC, go somewhere else. I'm just trying to briefly go over why I bought the laser.